Hi everyone, my name is Wei Yun.
And I'm Zhongyun.
I'm Qingchen.
In this project, we aim to extend our default project to investigate style transfer, where the inputs are black and white enemy sketches, and the output will be the colorized version. And in this project, we mainly focus on three popular style transfer methods, namely DC GAN, pix-to-pix, and cycle GAN. The DC GAN is a naive version, but very classical, and the latter two are relatively new and more advanced method. And in this project, we also investigate the effect of different data augmentation, different loss functions, perceptual loss or pixel-wise loss, and different architectures inside the GAN network. To begin with, we would like to go over some background notation used in our project. The first one is the difference between the unconditional GAN and the conditional GAN. So compared with unconditional ones, conditional GANs will directly observe the input images. So the discriminators will condition on these input images to tell if the images are fake or real. And the DC GAN is a very classical method that was firstly proposed to replace the pooling layer inside the architecture with the strided convolution, upscaling or downsampling the in-between feature images. And it also used batch norm in both the generator and discriminator. And it had some marginal improvement at that time.
So the pix-to-pix network firstly proposed to use a conditional GAN to solve the general purpose image-to-image translation problems, such as super resolution image inpainting and style transfer, the one we're investigating in this project. And cycle GAN builds on top of pix-to-pix, where it introduces cycle consistency so that style transfer or image-to-image translation can be done without paired data.
So the data set we are using is a paired data set. So our aim is to transform the sketched image at the right to the colorized one using the GAN. And so we have proposed several methods. The first one we introduce is to modify the loss into VGG loss. As we can see from the formula, C represents the color channel, H is the height, and W is the width. This is a kind of perceptual loss that capture the perceptual quality instead of the L1 loss, which only captures the pixel-wise loss quality. And next.
The second change we made was with the pix-to-pix and cycle GAN generator structure. So in the default repo, both pix-to-pix and cycle GAN use a ResNet with 9 blocks for their generator. And we thought because ResNet usually gets better than the usual VGG when the network structure gets very deep, for example, 19 VGG or 30 layer VGG. And we thought the 9 block network might not be deep enough that we need the skip connection. So one of the experiments we did was to eliminate skip connections in the generator.
Finally, we decided to investigate the performance of data augmentation. Specifically, we choose to augment our data using online techniques such as randomly flip it horizontally or randomly rotate it by a degree from -5 to 5 degrees with a probability of 20%.
So below you can see our experiments and results. We measured both quantitatively and qualitatively. With quantitative measurements, we used FID and KID, both metrics, both with lower scores the better. And our best results actually came from pix-to-pix with VGG loss replacing the original GAN loss. And as you can see from the right side is our qualitative results, where the first row, the first picture here is our input sketch, and the first row shows all the DC GAN baseline results. So for example, on first row, second column, we see DC GAN baseline and followed by DC GAN L1 augmentation and DC GAN L1. As you can already see, DC GAN is not very robust to various forms of inputs. For example, this is just one random input image that we chose, and DC GAN already outputted something that doesn't make any sense with only one loss. On the second row, we can see all the pix-to-pix baselines and our modifications. So from left to right goes from pix-to-pix baseline with data augmentation, with VGG loss, and with no skip connections. We can see both that baseline and data augmentation and VGG loss performs relatively well on this task, but as opposed to what we originally thought, deleting the skip connections doesn't work that well. On the third row, we can see all the cycle GAN results going from baseline to adding data augmentation and with ResNet and no skip connections. Again, adding data augmentation improves the baseline, but deleting the skip connections doesn't work as we imagined. And finally, we just have the real output image. So here we thought why deleting the skip connections didn't work was that, as opposed to what we thought, the generator and discriminator structure was actually complicated enough that we needed to delete. We needed to add those skip connections in order for the back propagation to work properly. And that concludes our presentation. Thank you so much for listening.